In this section 6.6, Center of Mass, we're going to see how calculus is used to calculate the center of mass of various objects. We're going to start off with defining center of mass and showing how we get that without calculus, and then we're going to extend that definition to types of figures where we must use calculus to find the center of mass. So let's take a look at these two pictures first. So we have pictured here the same seesaw with a 75-pound weight on this right-hand side and a 50-pound weight on the left-hand side. So clearly, if the fulcrum, the balance point, is right in the center of the seesaw, it's going to tip that way if we put the heavier weight on this side. So what we're trying to figure out is where we should move that fulcrum so that this will balance. So let's call this distance right here that the fulcrum, to be consistent with the book, we want to label this distance as x. The total length of this seesaw is 10 feet. So that would mean that this distance from the fulcrum to this other end of the seesaw would be 10 minus x feet. And we call these products the distance times the force times the distance from the fulcrum. We call these moments because, I'm not sure if there's a because answer, but they're called moments, and they are, this right moment is a force that would swing the seesaw that way, and this left moment, 50 times x, is a force that would swing the seesaw that way. So if we have the balance point, the force or the weight of the 50-pound object times its distance from the balance point, that moment, 50x, should equal the 75-pound weight times its distance from the balance point, 10 minus x. In other words, the downward moment to the left would have to equal the downward moment on the right side. So let's solve this for x. We get what? 50x equals 750 minus 75x. 125x equals 750, or x equals 6, and makes pretty good sense. You can't quite see it because the perspective is a little bit different, but we're looking at things on a little bit of an off angle, but it should make sense that if this distance is 6 feet and this distance is 4 feet, then this object would balance. So let's let's do another example showing how we calculate moments when we're in 2 dimensions. I should say one thing before we move on. We're assuming here that all of the mass is at a point right on the end of the seesaw. So the 50-pound mass is here, the 75 here, and in the balance figure, everything is positioned there and there. So let's move to 2 dimensions and see how things work, how we find we actually have to then find an x balance point and a y balance point. So let's move to the next blackboard. First, let's note that what we just did is found on the page 131 in your text. And what we're going to do next is found on page 132. So in this example, we want to find the balance point. It's actually already noted as being right here. For these 4 point masses, we're assuming that the mass, I've got them sized to represent how large they are, but they are the masses at a point, so they're at a point at the very center of those circles. So we've got represented here the masses 15, 10, 5, and 2, and the coordinates of the points where they reside. We've got an x center of mass, which we're going to call x bar, and a y center of mass. And the way we calculate these centers of mass, x bar and y bar, is to take all of the moments. So the moments for the x direction are going to be the weight times how far it is from the origin, plus the second weight, which is 1 unit from the origin, plus the weight 5, which is at the origin, plus the weight 2, which is 1 unit to the right of the origin. And then we normalize that by adding, or by dividing by all of the weights, which are 15 plus 10 plus 5 plus 2. The y center of mass is calculated the same way, except we're using the moments across the y-axis, right? So in the x case, we were doing these distances, right? How far it was from the x-axis, and the y, for the y center of mass, we are putting in how far the masses are from the, actually I said that wrong, right? For the x center of mass, we're seeing how far each object, each point mass is from the y-axis, and to calculate the x center, or the y center of mass that we're going to do now, how far is each point from the x-axis. So putting that information in, the 15 unit weight is 4 units away, the 10 unit weight is 2 units away, the 5 unit is at the origin, and the 2 unit weight is 3 units away, and we're adding, or dividing by the same denominator, which is what, 25 plus 7, 32. So if we do these computations as they are in the book, the x bar is 9/16, or 0.5625, and the it's negative 0.5625 minus 9/16, and the y bar is what, 74 over 32, which is approximately 2.3. And does that make sense? Well, we already said it's this point right here, and it makes pretty good sense that if we put weights of this, the 15, the 10, the 5, and the 2 pound weight here, and we say position them on a piece of paper, and then made the piece of paper horizontal and stuck a balance point under it right there, that it would balance. It should be pretty easy to visualize that. So in both of these examples, again, we had to assume that all of the mass is centered at a point, and we're going to extend that concept to see how we can find the point mass of an object where the mass isn't centered at a point. So let's take a look on the next blackboard at a picture for an object whose center mass we want to find. So we want to find the center of mass of this irregularly shaped region, and this region is defined in general to have a top curve that is f of x, and a bottom curve that is g of x, and we're trying to find the center of mass on the interval A, B. And we might guess that the center of mass would be, say maybe about right in here somewhere. So here's how we figure out the formula for getting the center of mass of an irregularly shaped object like this. So we take a representative slice of the object, a rectangular slice, and we assume that the center of mass of that slice is at the very center of the rectangle. Well, the very center of the rectangle will be the x value of the center of that rectangle. So let's mark that coordinate we're trying to find here as the center mass of that rectangle as x bar, y bar. So the x center mass is just x, and the y center of mass is going to be the average heights, which is going to be f of x plus g of x divided by 2, which is actually denoted in the picture and is on page 132 in your text, this setup that we're doing. So remember that the center of mass is how far that center is from the axis times its weight. So the x center of mass of the rectangle would be, I'm sorry, not the x center of mass, but the moment of the rectangle would be how far it is from the axis times the weight. Well, the weight would be the same as the size of this region. Actually, I left something out. We're trying to figure out the center of mass of this region, and the assumption that we need to make is that this region is a sheet called a laminate. It has uniform thickness, and so its weight is going to be proportional to its area, and it's going to be exactly its area times its density. So its area is the height of the rectangle, f of x minus g of x, and the density of that we're going to call this Greek letter rho, which is kind of like a P, except a P would be like this, and a rho we make from the bottom up like that with a curl in it. So that would be the x center of mass, and the way we get x bar into integral form is to integrate that across the region, put the rho outside, x, f of x minus g of x dx. Actually, let's slow it down just a little bit and do it like we did for point masses. So the x bar is going to be the rho times the sum of the x times the weight, which is f of x minus g of x, times the thickness. Go back here and put in, for this to be correct, we would need to put a delta x in here, right? And so going back to our previous formula, we took all of the moments that we had, right? Moments, all of the moments across the x-axis, and then we divided by the weight. So we're going to continue that process here, and so we're going to take each of the moments right, so the distance is x, and the weight is the area times the density rho. And we need to add up all of those moments. And then we also need to divide by the weight. And the weight is going to be everything that we have in the numerator without the x, right? So the rho is still there, and it's still f of x minus g of x times the thickness delta x, so it's the area times the density. It's not volume times density because it's uniform thickness. So we've got all of the moments in the numerator, and they're added up, and we've got all of the weights in the denominator, and they're added up. And just to be clear, the difference between the numerator and the denominator is that the numerator has this distance, this displacement in it. So we've done this a number of times now. We're going to this setup that we have right here only works if the mass really is centered in the middle of that rectangle. That's not going to be the case with this irregularly shaped region, but if the rectangle's widths get smaller and smaller and smaller, then the center of mass of the rectangle will be in the center of its rectangle. And what happens as that delta x goes to 0, it goes to dx, and so x bar becomes, right, goes to dx here, and the summation sign turns into an integral sign, and the rho comes out front, so it's this for the numerator, and the denominator is almost exactly the same. It's just that the x isn't there. We're just adding up the masses in the denominator, and the mass is the same as the density times the area. So the x is missing. Well, of course, we should get something similar for the y bar. The difference, though, is that the center of mass for the x with respect to the x coordinate was x, but the center of mass with respect to the y coordinate is this. So the setup for y bar looks a little different, and we'll do that on the next blackboard. So the y bar as a summation is going to be what? Instead of, remember we had x here, now we've got f of x plus g of x over 2 is the y center mass of the rectangle times the height of the rectangle times its thickness times the rho, and then we divide in the denominator by the same thing. Both of the x bar and the y bar denominators are exactly the same because it's just the mass. And so, as before, what happens as delta x goes to 0, the summation sign turns into an integral sign, and we do a little bit of algebra here to make this simpler. This is f a plus b times a minus b, and so we get this, we get f squared of x minus g squared of x dx over rho f of x minus g of x dx. So the process of developing these formulas comes from the point mass formula. We use the fact that we assume that we can find the point mass of this region by dividing it into rectangles, and the center of mass of each one of those rectangles is this, which is inaccurate because the curve is irregular, but as the width goes to 0, it becomes more and more accurate. So let's summarize our formulas. And let's notice that the rho is missing from both these formulas, right? Because in the x bar and the y bar case, we've got rho in the numerator and rho in the denominator. So here are our two formulas, which are nice in the sense that the denominator for both of them is the same. So let's take these two formulas and show by doing example 2 on page 133 that they're actually not so difficult to apply. So we're going to find the center of the mass of the region between y equals x squared, y equals x to the fourth, on the interval 0 and 1. And so this is our f of x, this is our g of x, and the x bar setup would look like what? Right? In the top, or the numerator for x bar, it's going to be x times f of x, which is x squared, minus g of x, which is x to the fourth, dx between 0 and 1, divided by integral 0 to 1, just top curve minus bottom curve dx. And the y bar, let's call this quantity right here our denominator, so we can use that again and not have to rewrite that. And then we can write y bar a little bit more simply as 0 to 1, and remember it was f of x squared minus g of x squared dx, and that's divided by our denominator d. So these are actually pretty easy integrals to do, so these problems generally are not too difficult because it's at least when we're working on polynomial functions, they're pretty easy to resolve. So here we're integrating what x cubed minus x to the fifth, right? And so in the numerator we get x cubed's integral, which is x to the fourth, x to the fourth over 4, minus x to the fifth's integral, which is x to the sixth over 6, between 0 and 1. And in the denominator we've got what x squared's integral, x cubed over 3 minus x to the fifth over 5, and that's evaluated between 0 and 1. In your book you see this is calculated at the bottom of page 133, and we get x bar is what's 15 over 24. And if we do the y bar setup, or the y bar computations on the next page, we get what the numerator is the integral of x squared is x to the fourth, x to the fourth squared is x to the eighth, and so if we integrate those, we get what x to the fifth over 5 minus x to the ninth over 9, evaluated between 0 and 1, and it's divided by that same denominator, and that number turns out to be 1/3. Okay, so let's note that first of all, I had to switch the coordinates of the points. I had them backwards, and the The x-center mass is just a little bit more than the halfway point, and the y-center mass, however, is only 1/3 of the way up. Let's look at these two regions, this region and this region, and note that that works as a balance point, because while this region right here, is actually stretched away further from the balance point. It thins out a little bit more, and it's a little hard to see because the areas are different. But kind of imagine that you're taking a weighted or a piece of paper weighted like this, and you stick a pin right at this balance point. Don't think of it as maybe as a piece of paper, but think of it as like a piece of heavy steel, and you're putting a balance post under it. You can kind of see that the moments on this right part and this upper part equal the moments on this left part and this lower part. But it's certainly not the center of the region, it's just the center of mass of the region. So we've done this one example of integrals applied to point mass. It wasn't a particularly difficult integral problem. The derivations of these formulas are a little bit complex that we went through here, but the point mass problems are pretty easy problems. So most of the example problems are very similar to this one that we did right here, so I'm only going to do this one example problem in this video. So that will conclude, or this will conclude this video on section 6.6 of the text.